Okay. In this video, we will explain about static memories. So, memories that consist of circuits capable of retaining their state as long as power is applied. That we will call as static memories. So, another type of memory is dynamic RAM. So, in the case of dynamic RAM, we have to dynamically refresh the memory to retain their value. But in the case of static memories, that retain their state as long as power is applied. There is no need to refresh the content. Okay. Then next we can consider the structure of a static RAM cell. Static RAM cell. RAM cell. We have to consider a single static RAM cell. So, this one is actually a static RAM cell. Two inverters are cross connected to form a latch. Then here then first we can consider how the value will be stored in this case of this latch. So assume that we have this is X and this is Y. If the state of the cell is 1, that means the X value is 1. Then what will be the value at this point? This will become 0. Because of this is 0, this will become again 1, then 0. This will be stabilized into 1 and 0. That means the state of the cell is now 1. We are considering the value at the point X. And another state is 0 state. We assume that the cell is at 0. Then what will be the content at Y point? This will become 1. Because of this is 1, this will become again 0, 1, 0, so 0 and 1. So this will be in a stable state 0 and 1, or we will call the cell contains a value 0. That's about the working of the static RAM cell. Then how it will be connected with our bit lines and word lines. So for that purpose we will use two transistors. This is one transistor and this is another transistor. Then this is our bit line. Okay, this is B and B bar. These are our bit lines. Okay. Then this cell, static RAM cell, or this latch is connected to the bit lines B and B bar through two transistors. We can call these transistors as this pass transistor. Pass transistor. Pass transistor, because this transistor will act like a switch, and whenever this transistor will become on, the content of the latch will be available here. That is the X point, the value at the X point will be available here, and if this transistor is on, then the content at the Y point will be available at the B bar line. That is why we will call this as pass transistor or switches. This will act as switches. Then assume that this is our word line. This is our word line. And these transistors are connected with this word line. Like this. Okay. So what happened? whenever this word line is activated, this transistor will become, this is actually a MOS transistor. We will call this transistor as MOS transistor. MOS transistor. These transistors are MOS transistor, and this one is also another MOS. MOS means metal oxide semiconductor. Metal oxide. MOS or metal oxide semiconductor. Metal oxide semiconductor transistor. Simply, they are MOS transistors. So we have two MOS transistors. We can call them as T1 and T2. So latch is connected to the bit lines through two MOS transistors T1 and T2, and the gate input of the MOS transistors are connected to wire line. So when this gate input will have some voltage, some high value, whenever this gate values will become high, this transistor will become turned on. T1 and T2 will become turned on, and the currents of the cell, currents of the latch will be available to B and B bar. That is, the value at the X point will be available to B, and the Y point will be available to B bar. So when the value on the word line will become 0, or this word line is not activated, this will become 0. Here we will have value 0. Then this switch, this transistor will be turned off. T1 and T2 will become turned off, and this latch will become disconnected from the bit lines. So the value will be retained there, and that will not reach into the bit lines. Let's go to read operation. Okay. This is the working of the how the static RAM cell is made. Then we can explain the read operation in detail. Static RAM read operation. Read operation. So the word line is activated first. So the transistors T1 and T2 will become activated, or that will be turned on, because the gate input to these T1 and T2 will become high, and these two transistors will become turned on, and the value at the X point will reach at a bit line B, and a value at a Y point will reach into bit line B bar, and that will goes into our sense amplifier or sense right circuit. So if the cell is in the stage 1, then B will have a 1, and here we will have a 0. And if the cell is in stage 0, then that value will 0 will reach into here, and this will be anyhow 1, and that 1 will reach into here. That's about the read operation. And the sense right circuits at the end of the bit lines monitor the state of the B and B bar and set the output accordingly. Okay, that's about the read operation. Okay. Then next we can consider about the right operation in the case of an SRAM cell. In this case, the state of the cell is set by placing the appropriate values on the bit lines B and its complement B bar and activating the word line. So the value to be written is placed on the bit lines B and its complement will be placed at a D bar. Then activate the word line. So that value, if you are placing a 1 here, then that value will reach here. Then its complement will be 0. That 0 will reach here, and we will activate the word line. So these two transistors will be turned on, and then 0 value will reach here. Then this 1 value will reach here. Then this 1, so this will become 0, 0, this will become 1. Then that will enter into a stable state 1, 0. That is the bit, the value presented in the cell is now 1. We'll take the value at the x point as the value of the cell. Then this is the same in the case of if you are using a 0 and a 1. In this case also, we will first place the value bit line and its complement accordingly, that is 0. We want to write a 0, then we will put a 0 here, then 1 here. Okay. Then we will activate the word line. So 0 will reach here, 1 will reach here, and then these transistors will become turned on. So this 0 value will reach here, this 1 value will reach here, then 1, 0, 0, 1. So this will end us to another stable state, that is x value is now 0, or we will say that a 0 value is stored into our S answer. Okay. And the required signals on the bit lines are generated by the sense right circuit, because the value actually to be written is received through the data lines that will reach into the sense right circuit, and then sense right circuit will make the bit lines to the corresponding values. Next we have to explain about the CMOS realization of these two inverters. Okay, this is the before discussing about the CMOS realization of a static RAM cell, we have to discuss about CMOS realization of a NOT gate. Then what is this CMOS? CMOS means complementary metal oxide semiconductor. CMOS, complementary metal oxide semiconductor. Then why this name complementary? Because in this we will use two type of transistors. This T1 is PMOS transistor and T2 is NMOS transistor. PMOS means P channel MOS. P channel MOS. P channel MOS. This is N channel MOS transistor. We are using both of these P channel, NMOS, PMOS and NMOS. That is why we call complementary metal oxide semiconductor technology. Then so this transistor is PMOS transistor and this is NMOS transistor. This is our PMOS transistor. PMOS transistor. This is gate PMOS transistor. So whenever the gate input is 1 or high voltage, then this transistor will become turned off and there is no path from this to this. Then when the value at the gate input is 0, logic 0 or low value, then this transistor will become turned on, and this will become connected. This will become connected. Okay, that's about the PMOS. In the case of NMOS, this is our NMOS. NMOS transistor gate input. When the gate input is a low value, this transistor is turned off and there is no path. And if the value at this gate input is a high value, then this transistor will become turned on, and then there is a path from this one to this two. Okay, that's about the NMOS and PMOS transistor working. Then we can consider the working of this our NOT gate. So actually this is our NOT gate. When here 1, output will be 0. Here, okay, if you are giving a 0, output will be 1. If you are giving a 1, output will be 0. And we can consider the same in our CMOS realization. So if you are giving a 0 value, what will happen? 0 will reach here, 0 will reach here. So this transistor will be turned on and this will be turned off. So there is a path like this, and V supply will be available at the output, or output voltage will be raised into, pulled into V supply. So here a 1 will be there. Similarly, in the case of applying one here, what will happen? Here 1, here 1. So this transistor will be turned off and this transistor will be turned on, and there will be a path like this. So the output voltage will be pulled down to ground or 0. So 1, 0. Then that's about the working of this CMOS realization of the NOT gate. Then a key feature of this circuit is that T1 and T2 operate in a complementary fashion. That is, when one transistor is on, other will be off. And there is no closed path between power supply, this V supply, and a ground. In both cases, when we are giving a 1 or 0, there is no closed path between supply and a ground. So this circuit does not dissipate appreciable power when it is in a steady state. So the power dissipation will be less in the case of this CMOS realization, because there is no closed path between supply and ground. Okay.